So a little bit of a recap of some fluids theory concepts that we saw introduced in our transportation chapter and which have come up in the lab. Now, here we've got a person sitting on a stool. There's three legs to the stool, and each leg is 1 centimeter in radius. That means it's a circle on the bottom, and so that has an area of pi r squared. And of course, there's 3 of them. Now, we want to find the pressure. Pressure is a ratio of force to area. The force in this case is just the weight of the 100 kilogram object. Now, we find weight by multiplying the mass by the gravity field. So that's going to be 100 times 9.8. Okay, so we can find the pressure. 100 times 9.8, that'll be in newtons. The area is 3 legs, and each one is a centimeter. That's 0.101 meters squared. Now, a newton per square meter is defined as a pascal, so that's the unit part. And when you work out this number, it's 1.04 times 10 to the power 6 pascals. 10 to the power 6 is mega, so we can write this as a megapascal. I'll just note that a pascal is a newton of force per square meter of area, as we saw earlier in the fluid section. Okay, so that's the definition of pressure. Now, here an idea. Atmospheric pressure. Here at the surface, the atmospheric pressure is 101.325 pascals. In kilopascal units, that's 101.325. And a couple of other common units, the good old imperial unit of pounds per square inch, 14.7 psi, and the chemistry unit, it's 760 millimeters of mercury. Now, why is it that the air at the surface is pressurized? Well, it's because of the weight of all the atmosphere above it. The atmosphere is 50 to 100 kilometers high, depending on where you draw the line. And all those little air molecules, air is not very dense, but all the way those air molecules squeezes down on the air at this surface. So the air we breathe is under pressure due to the weight of a column of atmosphere above it. Okay. Now, pressure gauges don't read the actual pressure, because if you detach this from the tire, it's going to read 0. What a pressure gauge reads is actually the difference between the pressure and atmospheric pressure. And this is called the gauge pressure. And gauge is just a device for measuring pressure. So if you have a pressure gauge on your bike tire and it reads 45 psi, that's the gauge pressure. We can find the actual pressure by adding, just rearrange this equation, gauge pressure plus atmospheric. Okay, so this was 45 psi. Atmospheric pressure, as we said on the previous page, is 14.7 psi. So that will be, in psi units, 59.7 psi. We could convert that to other units using the equivalents on the other page. Let's say we want to cancel psi and replace with atmospheres. Well, 1 atmosphere, as we saw, is 14.7 psi. So canceling psi and dividing, we get 4.06 atmospheres. I should just add that to the previous page, I suppose. Here I should say that atmospheric pressure is just 1 atmosphere, 1 atm. Okay, and we could likewise convert this to Pascal units. Because 1 atmosphere is 14.7 psi, it's also 101.325 pascals. So cancel off psi, convert to pascals. Okay, so thus far we've got the definition of pressure as a force to an area. We've got atmospheric pressure, 101.325 pascals, and the other units. Then we've got the idea that the gauge pressure gauge measures the difference between pressure and atmospheric pressure. One further idea that we'll be exploring in the lab is that pressure increases with depth. And so if we're going underwater, under the water, we've got the weight of the atmosphere here, and then we've got the weight of this much water. Say this is a whale down here. So there's two contributions to the pressure at this depth. There's the weight of the atmosphere up here, and then the weight of this much water. Now we did a derivation, and we showed that the extra contribution to the water depends on the density of the water, the gravity field, and the depth. So we could, for instance, find the water pressure 1,000 meters down in seawater. Now, fresh water would be 1,000. This is seawater, so the density is a little higher. So we substitute in atmospheric pressure, density of seawater, I'll put the units in. G is the Earth's gravity field, that's 9.8 newtons for every kilogram, and the depth we were looking for was 1,000 meters. Now, in terms of the units, kilograms will cancel, one of the meters will cancel, and a newton per square meter, as we said previously, is a pascal. So this is pascals plus pascals. And the answer that we get is 10,195,325, or 10.19, or 10.2 million pascals of pressure. And you could see on the chart, that's just here 1,000 meters. As you get deeper and deeper and deeper, the pressure increases to tremendous values. Now that's just part A. We'll do part B and C in class. One more here. Find the air pressure. So here's the surface of the Earth, and then here's a bird, here's a tree. Oh, sorry, that looks like a person. A tree. There's a tree. And we're up here at an altitude of 2.5 kilometers, so we're 2,500 meters up there. What's the pressure up here? Well, we know pressure increases with depth, right? So if this were the water's surface, then the pressure would get bigger as you go deep in the water. Right here at the surface, it would be atmospheric pressure. So as we go up, we expect the pressure to decrease, because we know it increases as we go down, so it should decrease as we go up. Now, when we're in the air, there's a relationship that gives us the pressure as a function of height. If we use Z for the height, then the pressure at height Z is the atmospheric pressure times an exponential function. Now, E is the natural anti-logarithm. It's 2.71828. It's just a constant, and you'll use the e to the x key on your calculator. And Z is the height. Now, h here, e to the minus z over h, that's up in the exponent. H is a constant, which is given. It's known as the density scale height. And that scale height is expressed in meters. So Z is the actual height, or the altitude, and that's also in meters. The P naught is just atmospheric pressure. So the pressure as we gain height Z can be found in this way. So we put in the given height, which was 2,500 meters. Now we were told the scale height was 8 kilometers, so that will be 8,000 meters when we convert. So I've got to do 2,500 divided by 8,000, make it negative, and then do the e to the x. This is a terrible calculator, but I'll try showing you here. So it's 2,500 divided by 8,000. Then we're going to make it negative. And then I've just got to store that in memory. And then I'm going to do e to the memory recall power equals. Your calculator has a much better way of doing that. But I'm going to multiply by 101,325 to get the answer. 74,131 pascals. So pressure decreases with height. And when we're in the air, we use this relationship. So because water has a uniform density, we have this simple relationship to describe the variation of pressure with depth. Air doesn't have a constant density. You can see on the graphic, right? The air molecules are more pushed together here. A gas is very compressible. And that's why we have a more complicated pressure relationship. So those two equations govern the relationship of altitudes or heights or depths and the pressure. Now when we meet in class, we'll do a few more examples on this, then you'll do a quiz. And I emphasize this is not on the midterm. This is just to support your understanding both in the lab and also in later water courses in your program.